Let's jump right into this explainer because today we're tackling something that literally shapes global geopolitics, energy, and security. We are demystifying uranium enrichment. So I want you to picture a simple piece of uranium ore. Just a rock. You can find it naturally in the ground, in the soil. Honestly, believe it or not, it's even floating around in seawater. Right out of the earth, it's just low-level radioactive, super unassuming. But locked inside this completely ordinary-looking rock is a level of power that is almost incomprehensible.
Okay, let's dive into this, because this is where the story gets incredibly intense. With the right process, this literal dirt, this simple rock, faces a very stark fork in the road. On one hand, we can harness it to fuel and light up an entire city with clean energy. But on the other hand, it has the capacity to absolutely destroy that very same city. Two totally unimaginable extremes, and they both stem from the exact same starting point. Let me show you exactly how this actually works.
Section 1. The magic 1%.
So, to understand the journey of this atom, and frankly why natural uranium is pretty useless at first, we have to talk about isotopes. Just as a quick refresher, isotopes are basically natural forms of an element that have identical chemistry but slightly different weights. This leaves scientists facing a monumental task. They somehow have to separate materials that look, act, and behave exactly the same, aside from this tiny, microscopic difference in mass.
And this brilliantly illustrates our ultimate needle in a haystack problem. See, over 99% of natural uranium is an isotope called U-238. And honestly, it's just too heavy and too stable to be useful for generating energy or building weapons. The magic sliver we actually care about is called U-235, and it makes up less than 1% of all natural uranium. No kidding, less than 1%. So this entire massive quest of uranium enrichment, it's solely about isolating that tiny microscopic fraction of U-235.
Section 2. From rock to gas.
Now, before we can even try separating out that 1%, we have to completely change the physical state of our material. Because, well, you obviously can't separate solid rocks based on microscopic weight differences. So the rock goes through this incredible physical and chemical transformation. First up, the raw ore is mined out of the earth and crushed. Then it gets treated with a series of chemicals until it becomes this coarse powder that experts call yellow cake. But we're not done yet. That yellow cake goes through two more complex chemical reactions until it transforms into a white crystal called uranium hexafluoride. And here's the kicker. When you heat this crystal just slightly, it turns into a gas. It has officially gone from dirt in the ground to a gas, fully ready for the next crucial phase.
Section 3. The spin room.
Okay, this is where the actual mechanical wizardry takes place. This is where that microscopic difference in weight finally becomes our key to unlocking the power of the atom. That uranium hexafluoride gas we just talked about, it gets pumped into these highly specialized machines called centrifuges. Picture these tall cylinders, and they're spinning at mind-boggling speeds. We are talking over 1,000 times per second. It is an incredibly violent, intense environment, and it's designed for one highly specific purpose.
Now, what's really interesting about this slide is that despite the extreme engineering involved, the physics are actually surprisingly straightforward. Because the centrifuge is spinning so incredibly fast, the heavier, completely useless U-238 gets thrown hard against the outside wall of the cylinder. Meanwhile, that slightly lighter, highly coveted U-235, it stays right in the center, where it can be carefully collected. But of course, there's a catch. One single centrifuge barely does anything at all. The separation is so minuscule that you can't just spin it once and call it a day. To actually make it work, you have to link hundreds of these centrifuges together into what's known as a cascade. They run the gas through one machine, collect that slightly richer gas from the center, pipe it directly into the next machine, and do it over and over and over again. They're basically constantly running it through to climb the concentration of that U-235.
Section 4. The enrichment scale.
As that cascade keeps spinning, we hit some very specific milestones. And as you can see, as the percentage of U-235 climbs, the stakes escalate dramatically. When you reach between 3 to 5% enrichment, you've got your standard nuclear fuel. That's enough to power a commercial reactor and safely light up an entire city. Now, if you keep those cascades running and push it above 20%, you get highly enriched uranium, which is typically used in specialized research reactors. But if you keep going all the way up to 90%, that is weapons grade. At 90%, you literally have a nuclear bomb. The final destination is entirely determined by just how far you push the scale.
Section 5. The terrifying math.
So the crucial point is that this process is absolutely not linear. Taking that natural ore from roughly 0.7% up to 60%, that is the incredibly hard part. We're talking years of continuous spinning and thousands upon thousands of centrifuge hours. But jumping from 60% up to that 90% weapons grade mark, that doesn't take years. No way. That last step can take mere weeks. Why? Because the hardest work, stripping away the vast majority of that useless U-238, is already done. By the time you hit 60%, you are almost already there. The leap to a weapon happens in the blink of an eye.
Section 6. A dial, not a wall.
Once that desired enrichment level is reached, we finally arrive at two distinctly different physical choices. If the goal is peaceful energy, that slightly enriched uranium gets converted into a fine black powder. That powder is then pressed into safe, small ceramic pellets and loaded into a nuclear reactor. It's heavily controlled, exceptionally safe, and incredibly powerful. But if that enrichment is pushed past 90%, it skips that step entirely. Instead, it gets compressed into a dense metal core. And that metal core is the material for a nuclear weapon. What's absolutely vital to grasp here is that it's the exact same element and the exact same process, right up until that final critical choice.
And this brings us to a quote that I think perfectly captures everything we've just covered. The line between energy and weapon isn't a wall, it's a dial. It's a continuous spectrum. And this dual-use reality, it's exactly why uranium enrichment is quite literally one of the most closely watched activities on the entire planet.
Which leaves us with a massive question to ponder. How do we safely monitor a dial that turns so quickly, knowing that the final, most dangerous leap from 60 to 90% can happen in a matter of weeks? It presents a staggering geopolitical challenge for us. Understanding how this science works is really the very first step to understanding why it matters so much to our world. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you on the next one.